Hi, Koji. I hope you can hear me.
Yeah, yeah.
I think someone should make you a co-host. Hi, nice to see you.
Oh, yeah. Yes.
I think someone should make you a co-host so you can start sharing your screen.
Okay.
But I don't think I have this privilege. Oh, now I'm co-host. Okay.
Okay. Okay. Now it's
okay. And
to try to share. Okay.
I think I should give you a permission to do it.
Hi, Shauli here. Sorry, there were some issues with our administration, changed again some setting in Zoom.
Okay.
So I'm trying to fix it with them. But
Okay.
I think I have made both of you co-host, and I checked with Koji.
Okay.
His slides worked. He has
Yes,
already shared it
Koji,
with me.
Koji, you're co-host now, so you can start
Okay.
sharing the screen.
Okay. So, where?
Share screen. Bottom.
Seems there should be a green button at the bottom.
Oh, sorry. Oh.
So I will come back to you again. Let me really.
Yeah. Yes, here.
Yes, but the size is wrong.
Yeah. Oh, which?
What did you say? Full screen? Maybe it will fix it.
Yeah, but okay. So sorry. Where is my? Wait. So I have some trouble. So where is my? Sorry. Wait a minute. So what? Okay. So okay. So yeah. And yes.
Still not right.
Something strange.
Yeah.
Somewhat wrong.
Did you choose full screen?
No, not yet.
Try to choose full screen. Maybe it will fix it.
Here? Oh.
Yes, perfect. Okay.
Fine?
Yeah,
okay.
Perfect. Thank you. Okay, and we still have 5 minutes.
Okay.
Are you in the office or home?
Yeah, this is home.
So you're not allowed to go to your office. So how is it in Japan?
Sometimes, of course, I will go, but today, because the Wi-Fi condition is not good in my department. So.
Okay.
Koji.
Oh yeah. Hi.
Igor.
Hi.
Yeah.
Hello, sir. Hi. Yeah. Hello. Yeah.
So I will introduce Professor Sparlinsky and hand it over to him for chairing this session, maybe in a minute's time.
Yes, I think you still have a few minutes.
Yeah, so no, I will hand it over to you, and then it's up to you to start whenever you think it's okay.
Okay. Sorry, and to start recording, who is going to do it? Do you want me to do it? I don't know whether. I assume that recording is okay, right? If you record your lecture.
Yes, they are media. Our media is recording the lectures.
It also it says recording paused.
So they. Sorry, I could not understand you. Sorry.
So recording, who will start it? Do you want me to start?
Okay, so welcome everyone. Let me hand it over to you. Welcome everyone for the 4th day of Balu Fest. Today's session, morning session chair is Professor Igor Sparlinsky. So I will hand it over to him, and Professor Sparlinsky, you can take charge of the session. Thank you.
Okay, thank you very much. It's my pleasure to chair the first session on this very special day, which is actually the actual birthday of Balu. So I suggest we all start with unmuting and clapping in his honor. Hey, happy birthday.
Thank you very much.
And now it's time to start our first talk. So Koji Matsumoto from Nagoya University will give a lecture on the behavior of multiple zeta functions with identical arguments on the real line. Okay, Koji, please.
Okay. So thank you very much for the introduction. So today my talk is, as in the title, so to discuss some behavior of multiple zeta functions, but on the real line. And this is a joint work with my young colleague, Toshiki Matsusaka at my same university, and also the Ilya Taneskov from Serbia. Okay. But first of all, oh, what happens? Oh, yeah. First of all, I'd like to express my congratulations to Professor Balu. And I remember that when I started my career, when I was a first year graduate course student, my supervisor suggested me to read the paper of Balu. So my first paper, the master thesis, was strongly influenced by his paper. So in this sense, I'm strongly influenced by Balu's. So I wish he's further long, happy, healthy, fruitful years. Yeah. Okay. Okay, let's go to the somewhat strange. So why the page is not going to what happened?
I think you can use both your mouse or the navigation buttons.
Yeah, but it's strange. The page did not proceed. Oh, what happened? Oh, I'm sorry. So there's some trouble?
Koji, are you using a laptop or a desktop? Do you have a mouse?
Yeah, no. I have some, there's no mouse. Oh, strange.
Koji, can you use your cursor?
Yeah.
Let's try that. Cursor is not working.
No.
You may try logging out and then coming back.
Yeah, that's a possibility.
Okay, so first I will first I will stop my share and I will try again. Okay.
Okay, let's try it.
Okay. So then. Okay.
Okay.
Oh no. Why? What happened? So I'll once more try.
Hello, maybe you can try to share the desktop, not the application. Did you share the application or the desktop?
Desktop, yeah, desktop here. My file is already in the desktop, and I now choose that one, and try to share that. So then it's shared. Can you see my my slide?
And so this is sharing the application directly, the application or the desktop?
Desktop.
Desktop, okay.
Yeah. But oh, strange. It moved. What happened? I've never encountered such situations.
Maybe you can put it all off and start again. Just disconnect and start again. I do that sometimes.
Disconnected. Okay.
I do that sometimes.
Okay. So I'll first go out from the room.
Yeah.
Okay, I'm coming again.
Yeah.
And so I will try once more.
Maybe as Alina said, you can try to share your desktop.
Desktop, yes. It's
Okay.
already on the desktop.
Okay.
Oh,
It is visible.
but still don't
Still
move.
don't want to navigate.
松本先生、
はい
なんか、デスクトップ全体を共有するか、またはアプリケーションだけ共有するか、多分選べると思うんですけど、で先生は今はどちらから共有してるんですかね。
デスクトップ。
デスクトップ全体ですか？
全体というかデスクトップの中の一つを選んだわけ。
じゃあ多分それはなんかアプリケーションだけ共有することになっているので、デスクトップだけ選ぶと、
ちょっと待って、じゃあ、分かった分かった。ちょっと待ってね。
すいません。はい。
だからHow about?
What is the problem? You are not able to share it, Koji?
Okay, now, yeah. So I want to try again.
Okay, please go ahead.
No, the pages are not moving for him. He can share, but from second page, he is not able to go to third page.
Can you click on the third page maybe by your, yeah.
Yeah?
Yes. Then
works.
do like this. Yeah.
Yeah, now we can go slide by slide.
Yeah.
Okay, you can see?
Yes.
The second page, okay?
Yes.
Good, okay. So now I will go to the third page, okay? So let's start the mathematics. Okay. So now, my talk is about the multiple zeta function, but I start with recording the very basic fact about the Riemann zeta function. Because on this page, everyone knows the matter, but I will start from this point. That is Riemann zeta function is of course convergent absolutely in the half plane. The real part is s is greater than 1, and is continued metamorphically to the whole space, and the only pole is s equal 1, and the zeros, as you know, so there is no zero in the convergent half plane, and in the plane negative half plane there are trivial zeros, so-called trivial zeros at the negative even integer points, -2, -4, -6, and all other zeros, as you know, in the strip in between 0 and 1. And of course, but famous Wayman hypothesis conjecture that they are all on the real line, the line, vertical line, the real part S is 1/2. Okay. So, however, in the case of the Hurwitz zeta function, so it's defined by the shift of the each term of the Riemann zeta function by the some real parameter alpha. In this case, usually the distribution of zeros is totally different from the case of the Riemann zeta function. So of course, when alpha equals 1 or 1/2, it is essentially the Riemann zeta function. But except for these two cases, the situation is very different. In particular, complex zeros are very very distributed, and in particular, the Riemann hypothesis, analog of the Riemann hypothesis, does not hold. But today, my talk is not on the complex zeros, but I'm watching, and today I'm reporting on the real zeros. So therefore, first I will mention some history on the study of the real zeros of the Hurwitz zeta function, which has been studied extensively by recent years. So the first, Takashi Nakamura, 5 years ago, proved that Hurwitz zeta function has at least one real zero in the interval between 0 and 1, if and only if alpha, the parameter alpha is less than 1/2. Okay. And then the next year, the Nakamura obtained the analog of his result in the interval between -1 and 0. And next, Toshiki Matsusaka, who is actually one of the joint authors of this talk, extended Nakamura's criterion to all intervals -n, -1, and -n. So all negative intervals of length 1. And he gave a criterion of the existence of the zeros in this interval in terms of Bernoulli numbers. For example, in particular, he showed that there is precisely 1 0 in the interval in between -2m, -2m, -2, and -2m. Okay. And then in 2019, Kenta Endo and Yuta Suzuki refined Nakamura's result to show the following. So in Nakamura's work, he proved the existence of the real zero, but he didn't mention the number of zeros. But Endo and Suzuki proved that actually the Hurwitz zeta function has precisely one simple zero in the interval between 0 and 1, if and only if alpha is less than 1/2. And moreover, if we denote this simple zero as beta alpha, then beta is. So as a mapping, it's strictly decreasing C infinity diffeomorphism, and also it satisfies that asymptotic formula, beta alpha is equal 1 minus alpha plus, etc. Okay, so now by this work, we now know rather detailed information on the real zeros of Hurwitz zeta functions. So therefore now we are going to our target, multiple zeta functions, which is the Euler-Zagier R-fault zeta function, which is defined by this multiple series. And this is, for example, this is convergent absolutely in this indicated region. It can be continued meromorphically to the whole space, R-dimensional complex space. And also, its singularities are already completely determined. It's written there, SR equal 1, SR minus 1 plus SR equal 2, 1, 0, minus 2, minus 4, minus 6, etc., and so on. So the singularities are, at least its locations are now known. So how about the zeros? Of course, the investigation of zeros is more difficult. And the simplest case is, of course, the double zeta situation. Zeta2 S1 S2 is defined by this double series. And this was, I think, first studied by a paper of myself and Mayumi Shoji, which consists of two parts, part 1 and part 2. And this, the title of this paper is Numerical Computations, but actually this paper includes both numerical investigations and theoretical discussions. And in part 1 of this paper considers a case S1 is equal to S2, that is the one variable situation. So in this case, zeros are just isolated points. But in part 2 of this paper, we consider the general two variable situation. S1 and S2 are moving independently. So therefore, this is the two variable functions. So the zero sets, some analytic sets, hypersurface, etc. So it's more complicated. And the basic tool of this paper is a very simple but important fact that is so-called harmonic product. That is, so the product of two Riemann zeta is, you can see by just by definition, is written by this double sum, M1 and M2, and we divide this sum according to the condition M1 equal to M2, M1 is less than M2, and M1 is larger than M2. Then the first sum is equal to the nothing but the Riemann zeta of S1 plus S2. And the second sum is a double zeta. And third sum is also double zeta with the order of variable change. So this is valid for any S1 and S2, but in particular, if S1 equals S2, which we denote by S, then the last two terms, zeta2 S1 S2 and zeta2 S2 S1, both are equal to zeta2 SS. So therefore, we now obtain the formula that is zeta2 SS is written by in terms of the Riemann zeta function. So therefore, by numerical computations and of theoretical discussion, this is quite a nice formula because zeta2 SS is reduced to the properties of the Riemann zeta function. And by using this formula, we can observe. First, zeta2 SS has two poles at s equal 1 and s equal 1/2, because there is a factor zeta s and zeta 2s. The pole s equal 1/2 is coming from the factor zeta 2s. And also, it is easy to see that the points and negative even integer points are also zeros of this double zeta. And one more, each interval in between the two negative even integer points, each interval includes at least one more real zero. This can be proved by a simple just calculus, because by considering the derivative of zeta 2 SS, which is that one. And from this formula, we can find that at a point s equal minus 2L, the derivative of zeta2 is just minus zeta prime or minus 4L. But this is actually negative, which can be easily observed because of the simplicity of the trivial zeros of the Riemann zeta function. And so the derivative is negative. So therefore, zeta2 SS is decreasing at this even integer point, which gives the conclusion. So these are quite simple observation from the fundamental formula, which is the first line of this page. And of course, by using this formula, we can also compute the complex zeros, the distribution of complex zeros of zeta2 SS, which is mentioned in the aforementioned paper. But my aim is to consider the real zeros. So I don't want to discuss the complex zeros anymore in this talk. Okay. So today, my aim is not only the double zeta function, we will study the behavior of R variable, R-fold multiple zeta function, but all variables are the same, SSSS. And especially we consider distribution with real zeros on the real line. So this is a result in the paper of myself and Matsusaka and Taneskov, and which is already posted in the archive. Of course, this is, I think this is just the first step of the investigation of the zeros of the multiple zeta function. So of course, how about the complex zeros? And of course, more important is how is the situation in general multiple case? Everything is remains. So these are problems in the future. But anyway, today we consider the reduced situations. All variables are the same and on the real line. Okay. So in this investigation, the basic formula is written there. R times zeta R SSSS is equal to the summation of j equal 1 to R minus 1 to the j minus 1 zeta R minus j SSS and the Riemann zeta of JS. This is in previously I already mentioned the harmonic product formula, and this formula is also proved in similarly something like the harmonic product formula, or it can be also deduced from the classical identity of Newton. But anyway, this is our basic formula today. So hereafter, I quoted this formula as a fundamental formula. Okay. And so we will consider the behavior on the real line, but first consider the simplest situation, that is the case S is greater than 1. So this is, in this case, this is a domain of convergence, absolute convergence. So the definition series is valid in this region. So everything is quite simple, because from this expression, it is easy to see that our zeta R SSS is monotonically decreasing. And when S tends to plus infinity, this value tends to 1 or 0. Tends to 1 just in the case of the Riemann zeta function. And when the R is not less than 2, it tends to 0. This can be easily observed from the just by the definition series. And probably we can consider more closely. We can even show that the asymptotic behavior when S tends to plus infinity is actually asymptotically equal to R factorial to the minus S. And also, moreover, for any fixed S, then the value of zeta R SSS tends to 0 when R tends to infinity. So these results can be all can be proved without not so difficult from the very definition series. So anyway, this is a rather simple situation. So, okay, now we are going into the more difficult situation. So first, consider poles. We already mentioned that the double zeta function zeta to SS has 2 poles, S equal 1 and 1/2. And as a generalization, we can prove the following theorem 1, that is, the zeta R SSS has poles only at S equal 1 over K. K is between 1 to R, that is S equal 1, 1/2, 1/3, 1/4, and blah, 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 and finally 1 over R. And order of those poles are the integer part of R over K. So therefore, we can find the asymptotic formula, the ZR SSS is asymptotically equal to some constant times ks minus 1 to the minus integer part of r over k. This proof is still not so difficult. So when r equal 1, this is the limited case, it's clear. So therefore, we prove the theorem by induction. And recall the fundamental formula, this one. So maybe divide both sides by r. And we separate the part j equal r in the last part. Because when j equal r, zeta r minus j is zeta 0. Zeta 0 SSS is we regard as it's just one constant one function. So therefore, we obtain this expression, and then by the induction assumption, the pole of zeta r minus j SSS is just s equal 1, 1/2, 1/3, blah, 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 and 1 over r minus j. And also the Riemann zeta factor zeta js, of course, this has the poles at s equal 1 over j. So these are the all candidates of the poles. So therefore, it is obvious that the candidates of poles of this zeta RSS are just s equal 1, 1/2, 1/3, and 1 over r. Of course, the previous theorem includes the assertion of the order, and to prove this order assertion, it is necessary to discuss a bit more closely. But anyway, the assertion of the order of the poles also can be proved inductively. So this is a basic structure of the proof of the theorem 1. And in theorem 1, there is a constant CRK. This is, in this term, we just say this exists, just a non-zero real constant. But actually, this constant is explicitly determined. It's given by this theorem. So CRK is, so you can see, so CRR, CR1, CRK, etc. And the second, fourth formula, fifth formula, a bit complicated, but quite clearly it is given explicitly. So this result is also proved by induction, but not so simple. For example, to prove this theorem, first we prove the third first half formulas by induction, and then by using these formulas, we prove the second half by some kind of double induction. So the argument is a bit complicated, but quite so, how to say, some kind of exercise of calculus, etc. Maybe you can find that the second half formula implies that CRK has some kind of periodicity, not completely periodic, but some kind of periodicity modulo K exists. So it may be some interest. But anyway, we can, by this way, we can find rather explicit information on the behavior of the our multiple zeta function near the singularity point. Okay. Okay, now I will go back to the situation in between 0 and 1 later again, but before that, I will talk about the case when s is less than 0. So in this case, as in the case of the Riemann zeta function, we have the so-called trivial zeros. That is the zeta r of minus 2n, minus 2n, minus 2n. This is always equal to 0. This is we can regard this as the trivial zeros of the multiple zeta functions. So this is again immediate from our fundamental formula, this one, because the factor zeta js is when s equal minus 2n, this is of course 0 because of the trivial zeros of the Riemann zeta function. So therefore, just one thing we have to note is that zeta r minus j factor is not singular at that point. But this is already proved by our previous theorem that R minus J SS has poles only in some positive point. So the S equal minus 2n is not singular. So therefore, the 0 at zeta JS is not cancelled. So it shows that this zeta RSS is indeed 0 at S equal minus 2n. This theorem is actually not a new result. This result was already conjectured by the paper of Akiyama, Egami, and Tanigawa 20 years ago, which is a paper first established the meromorphic continuation of multiple zeta functions. And 5 years later, this theorem was first proved by Kamano. So anyway, but now we can say that this is immediate consequence of our fundamental formula. Okay, so this is a situation on the negative even integer points. So how is the behavior of odd negative integer points? This case is also obtained by this theorem. So when k is odd integer, and we consider zeta r of minus k, minus k, minus k. And in this case, it's not 0. And we obtain some asymptotic formula when k tends to infinity. That is, for example, if r is odd, then zeta r of minus k is asymptotically equal to r over 1 over r times Riemann zeta minus rk, or r equal to this one, zeta 2 minus k is asymptotically equal to 1/2 times zeta minus k to the square. And when r is even not less than 4, then again we obtain asymptotic formula. So therefore, by this last, for example, you can see from this last term, it is clear that the absolute value of such values at odd negative integer points are rapidly increasing as k tends to infinity. In particular, when when r is odd, so there is some oscillating factor. So therefore, so the values of zeta r minus k when k is moving is there is a rapidly oscillating situation. Okay. Proof is again by induction, and it's so, for example, using the fundamental formula, our fundamental formula, properties of Bernoulli numbers, or sometimes use some elementary inequality. This r minus j to the r minus j, j to the j is less than r minus 1 to the r minus 1 is very just elementary, and it is valid when this region. But for example, by using this inequality, we can discuss by just elementary, but not so trivial argument. Okay. Okay. So next. So by theorem 3, we know that there is trivial zeros of zeta r s s s. So that is s equal minus 2 n r zeros. But numerical computations show that there are actually more zeros on the negative year line. And indeed, by from the data of numerical computations, we raise the conjecture that each interval minus 2 minus 2 n minus 1 includes r minus 1 real zeros, which are different from the so trivial zeros at integer points. This is our conjecture. At first, this was a conjecture, but then we noticed that we can prove this conjecture with only one exception. Actually, so for any n, not less than 2, in any interval, minus 2l, minus 2n minus 1, there are exactly r minus 1 real zeros. The difference of conjecture and theorem is the theorem cannot include a case when n equal 1. N equal 1 is just interval in between minus to 0. Only in this case is not captured by the following proof of the theorem. But anyway, almost all cases of the conjecture has now become a theorem. Okay. Okay, so I will state the proof with the theorem. So first consider the rectangle RK defined by this inequalities. The real part of S is in between minus 2 minus 2k plus 1 over R and minus 2 minus 2k minus 1 over R. And imaginary part of S is the absolute value is less than 1 over R. So this is a rectangle. And to prove our theorem, our fundamental tool is a Lucius theorem in function theory. So we are now proving some inequalities which is necessary to apply Lucius theorem. So first claim this inequality. Zeta RS over zeta R minus S JS zeta JS. The absolute value of that quantity is larger than R. This is valid for any S which is on the boundary of our rectangle RK. Okay. So to prove this claim, we use the functional equation of zeta S and find the following. Our quantity is written by a bit complicated, but anyway, sine factor and gamma factors and Riemann zeta factor. And we evaluate this right-hand side, each part of the right-hand side by some rather elementary argument. Sine factor and gamma factor is by using some basic calculus. We can evaluate the sine factor, gamma factor, and the Riemann zeta factor exists, but this is by the functional equation that this Riemann zeta factor is going into the domain of absolute convergence, so it is a bit more easily treated. But this argument is elementary, but by no means easy, using some directed tools such as the addition formula for the sine hyperbolic function or some infinite product expression with gamma function, etc. So elementary, but how to say, not so trivial. Anyway, by using those tools, it is possible to prove this claim. And then by using this claim, we can prove the following claim too, that is, on that boundary, the absolute value of zeta RSS is less than the absolute value of the Riemann zeta of RS. So this is again proved by induction. So when R equal 2, so zeta 2 SS is less than binary 1/2 times zeta 2 square plus zeta 2s. This is by using the fundamental formula. Then the part zeta square is less than by 1/2 times zeta 2s. This is by our claim 1. Maybe you can remember the claim 1. Claim 1 is here, this one, So when R equal 2, this is, and J equal 1, this is zeta 2s over zeta s square is larger than 2, which exactly implies this part. So then we find this is less than the absolute value of zeta 2s. So we are done. Similarly, when R equals not less than 3, ZRSS is first estimated by our fundamental formula. And then in the summation J equal 1 to R, we separate the part J equal R. And in the part J equal from 1 to R minus 1, we apply the induction assumption to replace that zeta R minus J SS is estimated by zeta of R minus JS. And then again, we use the claim 1 and to obtain our desired inequalities. So this is the proof of the claim 2. So therefore, now we again use the fundamental formula. We obtain the following inequalities. So the first line is, this is indeed the fundamental formula, and we again separate the fundamental formula, separate the part J equal R in the right-hand side of the fundamental formula to the left-hand side, and to take the absolute value of this both sides to obtain this one. And then in the second line, we use our claim 2. And the third line, we again use claim 1 to obtain this inequality. So totally speaking, so the left-hand side, R times zeta R SS minus something signature times zeta RS is less than the absolute value of Riemann zeta of RS. So this is a situation when the Lucius theorem can be applied. So therefore, by the Lucius theorem, the number of zeros of zeta RSS in the interior of our rectangle RJ is equal to that of zeta RS. But actually, because of the definition of RK, each RK includes one non-trivial zeros of the Riemann zeta function. That is, the number of zeros of the Riemann zeta function in the interior of RK is just 1. So therefore, zeta RSS is also includes just 1 0 in this rectangle, but zeta RSS is actually symmetric with respect to R. So therefore, if this is not a real 0, we should have the 1 more 0 as a complex conjugate point. So it is impossible. So therefore, this unique 0 in this rectangle should be real. So this completes the proof. Okay. Well, now we are going into the probably the most difficult part, that is that S is in between 0 and 1. And we already know that our zeta R SSS has poles at S equal 1, 1/2, 1/3, and 1 over R. So the remaining task is to consider the zeros in this interval in between 0 and 1. And first, we prove that in the smallest part, in the interval between 0 and 1 over R, there is no 0. This is theorem 7. Actually, zeta RSS is positive in this region for even R and negative in this region for odd R. This is again not difficult. This is again the immediate consequence from our fundamental formula. So when R equal 1, this is a Riemann zeta case So it is well known that the Riemann zeta function in the interval 0 and 1 is negative. So it is clear. When r equal to not less than 2, and when s is in between 0 and 1 number r, then we consider again, we consider the fundamental formula there. And we find, since s is less than 1 over r, so Js, Rs, those are still in the interval between 0 and 1. So therefore, zeta Js, zeta Rs, those are negative. Okay? And also the factor zeta R minus JSS, the signature of this factor is determined by the induction assumption. So therefore, by using those data, we know all signatures of all terms on the right-hand side, which immediately gives a conclusion. So this is just not so difficult. But this is only a simple case which we can determine the signature. And when S is larger than 1 over R, the situation is a bit difficult, more difficult. And we almost nothing can be proved. But here we can show some numerical figure. So when R equal 2, the value of the zeta 2 SS on the real line is as follows. This is a, maybe you can see the graph in between 0 and 1. The 1/2 is a pole of the double zeta function. And from 0 to 1/2, the double zeta is, you can see, the double zeta has no 0, it's positive. So this agrees with our 7, just we mentioned before. And in between 1/2 and 1, it looks like the double zeta function is monotonically increasing. So there's 1 0 in between, 1 real 0 in between 1/2 and 1. Okay. So the triple zeta we know the poles at 1/3, 1/2, and 1. And from 0 to 1/3, there's no 0. So the figure says that it is negative. But in between 1/3 and 1/2, and 1/2 and 1, it looks like that the function is monotonically decreasing. And so in each interval, there's 1 real 0. Okay? So we are going back to the double case. In the double case, the number of real 0 is in each short intervals, the number of real 0 is 0 and 1. And in the triple zeta case, the number of zeros in each short interval is 0, 1, 1. So how about the quadruple zeta? So in this case, the situation becomes a bit different. So in this case, the poles are 1/4, 1/3, 1/2. And from 0 to 1/4, there's no 0, it is positive. And in between 1/3 and 1/4 and 1/3, and 1/3 and 1/2, the graphs are monotonically increasing, and there is 1, 0. But in between 1/2 and 1, the figure shows that it go down and to the minimal point and go up to the infinity. So there is 2 zeros. So the number of zeros of this quadruple zeta in each short interval is 0, 1, 1, 2. Okay. So the fivefold. So in this case, so in almost all cases, the graphs are monotonically decreasing, but in between 1/2 and 1, it seems that there is 2 zeros. Okay. And finally, I will show the 6/4 zeta function. This is more complicated. So in this case, the poles are 1/6, 1/5, 1/4, 1/3, 1/2, and 1. And so in between 1/2 and 1, there are 3 zeros. The graphs go up and then once down to and go back. So in between the 1/3 and 1/2, it seems there are 2 zeros. And the remaining interval, it seems they have only 1 zeros. So the number of zeros in short intervals are 0, 1, 1, 1, 2, 3. Okay, so we will go back to the here. No, here. So the data is as follows. So let IRK be the number of zeros of zeta RSS in the interval S is in between 1/k and 1/k minus 1. So as I mentioned when we look for the graph, so in double zeta case, the number of zeros is 1, which is in the interval between 1/2 and 1. And triple zeta case is 1, 1. The quadruple zeta 1, 1, 2, 1, 1, 1, 2, 1, 1, 1, 2, 3, etc. And actually, I showed only up to the 6/4 zeta, but we computed to the 10/4 zeta. And according to the data, which can be obtained from those graphics, we raise a conjecture that for any double zeta function, all real zeros are simple, and the number of zeros in the interval in between 1/k and 1/k minus 1 is given by the integer part of R/k. This is conjecture, and this is still unproved. Maybe I will show one consequence of this conjecture. If this conjecture is true, then the total number of real zeros in the interval in between 0 and 1 is asymptotically equal to R log R minus 2 times 1 minus gamma R plus O to the R 1/2, where gamma is Euler's constant. And this is actually the simple consequence of the conjecture, because if the conjecture is true, then the total number is a summation of the integer part of R/k when k is from 2 to R. But this is, as you can see from the description, it is a summation of k equal 1 to R minus R. And the integer part is can be written by the summation of L less than R, and L is congruous to 0 modulo k. And if we change the summation of k and summation of L, you can find this is just equal to the summation of the divisor function dl minus R. So therefore, our result is it's nothing but the immediate consequence of the well-known formula for the symmetry function of the divisor function, summation of L less than R of dl. So of course, the error term, I just wrote error term O to the R, O of R to the 1/2, but of course this is not best possible. And today, I think the best known result is some exponent which is a bit less than 1/3 due to Martin Huxley. But anyway, we can show the asymptotic formula for the total number of real zeros. this conjecture is, so far I have no idea to prove this conjecture, and it's still open, but very recently, my student Kenta Endo obtained some partial result on this conjecture. Indeed, just 3 days ago, Endo presented his results in the number 3 seminar at Nagoya University. So his work is still in progress. But anyway, some simple case has been solved. Okay, so that's all. Thank you very much.
Okay, thank you very much for your talk. Let's unmute and clap. And the speaker. Any questions?
Yes, sorry, I do have a question.
Yeah.
Yes, go ahead.
In the last theorem you showed as an implication of the conjecture,
Yeah.
does it mean that we have some sort of equivalence with the sum formula for the divisor function, or so is the conjecture in some sense equivalence to this sum formula of the divisor function?
You mean some phenomenon concerning the divisor function is included in the theory of multiple zeta function? That's it?
Oh yes, yeah. I was just wondering. I mean, I think I didn't quite understand the last statement of the proof, but yeah, then I thought probably that's what.
I'm not sure. So. I'm not sure. So.
So then okay. So I think I didn't understand what you mean by this by the last sentence of this proof. So you said that this result follows from the well-known formula from
well, no, it's a spelling miss. But anyway, so, do you know that the summation of dl is equal to r log r minus etc.?
Oh yes,
yeah?
Yes.
Yeah.
Okay. So that's what you mean.
Yeah. Just
so
just
if you
I
replace.
applied. Yeah.
Yeah, I see. Okay. I thought.
Yeah.
I
Okay.
see. I thought that you could say something from the conjecture. Something more.
No, not
the
yet.
formula.
No.
Sorry. So I got confused. Thank you.
Thank you. More questions? Koji, may I ask a generic question? Has anyone tried to mix this with multiplicative characters and consider L functions of this type? And of
yeah. Yeah, I think it's possible.
Does it make sense?
Yeah. Probably some analogous statement can be proved. Yeah, it's an interesting direction, I think.
At least for the real characters.
Oh yeah.
Okay. Okay. Thank you.
Sorry, I have one question.
Okay.
May I ask a question?
Yeah.
Yes. Hello, Professor Matsumoto.
Yeah.
In the case of the double zeta function with two different variables, zeta of S1, S2, not S1 equal S2. So the real locus of the zero is an analytic curve in R2. Do you have any graph or any shape for these curves?
In that case, here you can see this second part, which is published in European Journal, and I don't show any graphics, but in this paper we have some, at least we have some. We proved some asymptotic behavior of that zero divisors.
But you do not have a graphic.
Oh, no graphic.
Okay. Thank you very much.
Yeah.
Thank you.
I have one question. Hey, Koji, thank you for a nice talk. So I wonder, so your fundamental identity is based on the fact that you can write zeta SSS as a polynomial in Riemann zeta values. Right? So I wonder, we have also other cases where we know that we can write them in terms of Riemann zeta values. For example, if you take S1 up to SR and then take the sum over all permutations of these Sj, then this is also a polynomial in single Riemann zeta values. So do you expect that maybe your strategy also works for these types?
Oh, no, I don't. I'm not sure, but I think I'm not optimistic.
Okay.
I don't think so.
I see. Thank you.
Thank you. No more questions? Okay, let's thank the speaker again.
Thank you.
And we'll resume in 2 minutes.
Yeah. Yeah, I'm just starting a video and yeah, just.
Okay.
Can you see? Oh, yeah. Can you see? Back. This. Can you see this? Can you see me?
Not yet. It's coming up. Not yet. Yes, you can see it now.
Yeah, now we can.
Okay. Okay.
Okay. We'll start in 2 minutes.
Yeah. You can hear me also, right?
Yes.
Hello, Sarda.
Hello. Hello, Balu. How are you?
Fine.
So you have taken your COVID vaccine?
Yes, yes. First one. One more I have to take it after 28 days.
I took 2 days back.
Oh.
I had some fever and all.
Oh, God.
You can see? Yeah, they can see. Okay, just call me if any problem. Yeah. Thank you.
Okay, I think it's time to continue. Let me introduce our next speaker, Saraja, who will be talking about rational points and certain superelliptic curves. Okay, please.
First and foremost, I would like to wish Balu many, many happy returns of the day. I like to thank the organizers also for bringing all of us in line on this online platform. Okay. Just 1 second. No? Yeah, just to use the scroller. So I'm going to call this Eder-Selpridge superelliptic curves. You will soon see the reason for that in a few minutes. In 2016, Bennett and Sixek considered rational solutions of x plus 1 into x plus 2 up to x plus k equal to y power L in x and y in rational numbers, x and y, with k greater than or equal to 2. There are at least 2 products on the left-hand side, and L greater than or equal to 2 a prime. So we always assume in this talk that L is a prime. They showed that if this equation holds, then L is bounded by e power 3 power k. And this can be considered as a rational analog to the classical Schinzel-Tiedemann theorem, a very famous theorem, transcendental number theory. So here is the result of Schinzel and Tiedemann from 1976. So consider fx equal to y power L, where fx is a polynomial with rational integral coefficients and with at least two distinct roots. Suppose the above equation has integral solutions in x and mod y greater than 1. Then L is bounded by a computable number depending only on f. By this dependence, I mean it may depend on the coefficients or the degree of f, anything connected with f. Okay. Bennett and 6x result that I mentioned earlier deals with the rational solutions when fx is the polynomial x plus 1 up to x plus k. So there are some trivial solutions to this equation x plus 1 to x plus k equal to y power L. So this, then by number 1, I mean this equation x plus 1 to x plus k equal to y power L. So it admits number of obvious rational points with y equal to 0, only -1, -2, -k, and also two infinite families of solutions given by x, y, k, l equal to a square by b square minus a square, ab by b square minus a square, k equal to 2, l equal to 2, and a not equal to plus minus b. And there is another family, x equal to 1 minus 2j by 2, y is plus minus 1 by 2 power g into product I equal to 1 to j of 2i minus 1, and k is 2j, L is 2. So these are solutions coming when L is equal to 2. And here A, B, and J are integers with J positive. There are two other solutions for this equation given by x, y, k, l equal to minus 4 by 3, 2 by 3, k equal to 3, l equal to 3. So it is a cubic now. Minus 2 by 3, minus 2 by 3, 3, and 3. And it is conjectured that there is no solution with L greater than or equal to 4. So you see that the solution, these solutions occur when L is 2, and in this case, L is 3. So apart from these solutions, it is conjectured that there is no solution with L greater than or equal to 4. And this conjecture is now known for K less than or equal to 34 by the works of several mathematicians. I will come to this a little later also. Here is a joint work with Pranavesh Das and Shanta Laishram from 2018. You consider this curve x plus 1 into x plus 2, etc., to x plus I minus 1, to x plus I plus 1, etc., to equal to y power L. So this curve is nothing but the original curve that I started with, except that there is one term missing here, x plus I, okay? And I varies now from 1 to k. So this one curve, when I varies from 1 to k, is going to give me k such curves, okay? And when I equal to 1, the endpoints, I equal to 1 or I equal to k, we are again back into that equation that I started with k replaced by k minus 1. So again, the bound for L, this exponent L, is going to be valid in these cases. So we will consider I varying from 2 to k minus 1. Okay? So our result is the following. When rational solutions for this equation with one term missing exist, what happens? So let pk be the least prime greater than or equal to k by 2. Then we showed that this equation, 3 is the equation with one term missing. So when this equation is valid with I varying from 2 to k minus pk, or I varying from pk to k. So I should lie either on the left side or on the right side of the product. Then two holes. Two is the bound for L, namely L is bounded by e power 3 power k. When k equal to 2q, in particular, where q is a prime, then you have this, the least prime greater than or equal to k by 2 is exactly equal to q. Okay, so we get the following corollary. So let equation 3 be valid with k equal to 2q, where q is a prime, then two holes. Because this condition that I has to lie between these two, this corner or that corner, it is valid in this case. And so the bound for L holds. So the condition on I, that it should be between 2 and k minus pk or pk and k, that has been removed subsequently after our work by Edis. And in 2019, I considered this equation with more terms missing. And in particular, I showed that if two terms were missing, then again, the bound for L less, that is L less than or equal to e power 3 power k holds. So let me show you how we proceed from this equation having rational solutions to equations which are in arithmetic progression. So let us assume that L is greater than K. This is not a very serious assumption, because our aim is to show that if there exists a rational solution, then L is bounded by some function of K. In fact, what we are at present having is a double exponential bound. So we can as well assume L is greater than K. Then write your x as n by s and y as m by t with m not equal to 0. I'm not looking for y equal to 0 solutions. And s and t, the denominator is positive. And the GCD of n and s is equal to 1. GCD of m and t is equal to 1. Okay, we can always write rational solutions like this. Then equation 1 can be rewritten as n plus s, etc., n plus ks equal to s power k into m power l by t power. And since the left-hand side is an integer, this is an integer now, so this has to be an integer, but m and t are co-prime, so t power l has to divide s power k, but we have also assumed the GCD of n and s to 1. So that gives you that s power k is actually equal to e power. So as L is a prime, using this assumption that L is greater than k, there is a positive integer d such that s is d power L and t is d power k. And in fact, this assumption can be relaxed, and you can see that the same conclusion that s is d power L, t is d power k, you can have even under the assumption that the GCD of L and k is 1. Okay, so you see that here is our equation, the original equation we have transformed into a product in arithmetic progression. These two cancel, so it is equal to m power L. So we have an equation of this form now. Z into Z plus T, etc. Z plus K minus 1 into E is equal to m power L, where Z is now an integer. The GCD of Z and D is 1, and this capital D is equal to D power L. It's a perfect LF power. So this delta, the product, is a product of k terms in arithmetic progression. So any solution to this equation with d equal to d power L will give rise to a rational solution to our original. So now by the results of Bennett, Giori, Haidu, and Pinter, it is now known that such an equation where one side is a product of terms from an arithmetic progression, when is it a perfect Lth power? This is now known, and in turn, the equation I started with has no rational solution if 3 less than or equal to k less than or equal to 34. So this is the result that I mentioned in the beginning. These are the mathematicians who worked on that. And L greater than or equal to 5. So let me now, so please remember this equation. So a product of k terms in arithmetic progression, whether it is a perfect power or not, that's what we are looking for. Let me go to some old results on this equation. Let us restrict ourselves to z greater than or equal to 1 in phi. So I'm looking for only positive integer solutions for the equation. Okay, and here comes a very remarkable result of Erdős and Selfridge from 1975, that this equation phi with k greater than or equal to 2 and p equal to 1 has no solution. That means a product of 2 or more consecutive positive integers is never a perfect power. So this is why we call this curve also Erdős-Selfridge curve. Their work opened a Pandora's box, and since 1975, several mathematicians have worked on this equation, the variations and extensions of this. Okay, so this Erdős-Selfridge theorem then tells us that the curve 1 that I started with has no positive integral solution. So let us now consider b greater than 1. Here, Erdős has a conjecture that this equation, where one side is a product of terms in arithmetic progression with d, the common difference greater than 1, implies that k is bounded by an absolute. So when k is bounded, then of course L will also be bounded by an absolute constant by the result 2. That is, L is less than e power 3 power k, so L is also bounded. This conjecture of Erdős is known under ABC conjecture by a result of Shorey for L greater than or equal to 5. And as I said, several mathematicians have worked on this kind of equation. There are variations and extensions of this equation. And there are nice expository articles by Shorey, and those who are interested may refer to them. Okay, so but for this lecture, I'm going to state 1 or 2 results from these old results. So let us write this D as D1 into D2, where D1 is the maximal divisor of D such that every prime divisor of D1 is congruent to 1 mod L. Okay. So then the every prime divisor of D2 is incongruent to 1 mod L, and the GCD of D1 and D2 is. We shall call this D1 as the L part of D. So the primes here are all congruent to 1 mod L. And in 2001, myself and Shorey, we showed that this D1 has to be greater than 1 for k greater than or equal to 4. K refers to the length of the product, and L greater than or equal to 3. So for cubes and higher powers, this D1 has to be greater than 1. Thus, you see that D1 is all its prime divisors are congruent to one model. So it has to be at least 7, implying that this equation in arithmetic progression equal to a perfect power does not hold if D is of the form 2 power A, 3 power B, 5 power C. So it has to have a prime greater than or equal to 7. Okay? So what is the implication of this for the equation when you consider it as a curve and looking for rational solutions? So then our original curve that I started with has no positive rational solutions in X and Y, whose denominators are composed of only 2, 3, and 5. Okay? In fact, about this D1, here I said it can't be of the form 2 power A, 3 power B, 5 power C. D1 is just greater than 1, we have said here. But we can find lower bounds for D1 and hence, of course, for D, depending on K and L. Okay? So improving upon my older results with Shore, I could recently show, for instance, that D is greater than or equal to D1 is greater than or equal to 1 over L, K power L minus 7 by L power 1/4 minus 7 by L power 3/4 for L greater than or equal to 7. So you can easily see that as L and K increase, the lower bound for D also increases. For instance, if K is greater than or equal to 35 and L is greater than or equal to 27, we get D as big as 10 power 16. So if an equation like that with a product of K terms in arithmetic progression should be an Lth power, then this says that the common difference has to be so large. Okay? So we conclude that, therefore, our equation 1 has a positive rational solution in X and Y. If it has, then either the denominators of X and Y exceed 10 power 16, or L has to be less than or equal to maximum of 20, because for L greater than or equal to 27, I have said, and L is the prime, so L has to be less than or equal to 23 and K. So this K is coming from the very assumption that I have assumed in the very beginning, that L is greater than K, so that I can transform this equation to an equation in arithmetic. So this is the implication of results of this type on equations in arithmetic progression being a perfect power on this rational solutions for the curve. And here you see that the bound for L is linear. So it is less linear in K. There we had the bound for L as double exponential, e power 3 power K. Let me state one more result here. This is from 1990 due to Shore and Tiedemann. So suppose K is sufficiently large, then the equation 5 with D greater than 1 and P delta greater than K. P delta means the greatest prime factor of this product, Z into Z plus D, etc., Z plus K minus 1 into. So the greatest prime factor greater than K implies that there exists a computable absolute constant C such that L power omega D is less than or equal to C times K log K by log K, where this omega D is the number of distinct prime divisors of D. Okay? So here you see the bound that they have got for L power omega D, and omega D is greater or equal to 1. So this is a bound for L itself. So L is less than or equal to C times K times log K by log K, which is very good. Okay. So you can view, but of course here K has to be taken very large. Right? So you can view this result of Shori and Tiedemann as being restrictive on K, but they get a very good bound on L, whereas the new results are less restrictive on K at the cost of a bound for L. Okay, so these are some general results on this equation. Now let me go to some small values of K when the length of the product is small. And in these cases, for many small values of K, one tries to solve the equation completely. In 1999, Sander and 2003, Lakal and Sander, they completely solved this one for K equal to 3, 4, and 5. And in 2006, Bennett, Bryan, Giori, and Haidu, they solved one for K less than or equal to 11. And Giori, Haidu, Pinter in 2009, they solved one for K less than or equal to 34. Okay. So let me now present a new result. So in a recent work, we consider this equation 3, that is the equation with one term missing. So x plus 1 to x plus I minus 1, x plus I plus 1 to x plus I power n. For 3 less than or equal to k less than or equal to 8, and 1 less than or equal to I less than or equal to k. So this is the result joined with Pranabesh Das, Shanta Laishram itself, and Divyam Sharma. We have almost completed it. We just need to give another reading. Okay, so let K be equal to 3. All solutions of 3 is just this equation, are given by K equal to 3, L equal to 2, I equal to 2. So when K is 3, it is just x plus 1, and I am omitting I equal to 2 term. So x plus 1 into x plus 3 equal to a square, L equal to 2, it's a square. So it will lead to some Pythagorean type of equations, and one can solve it, and you get some parametric solutions like this. And there is another K equal to 3, L equal to 2, I equal to 2. There are these type of solutions also. So here R and S are co-prime integers, R greater than S greater than 0, and they are of opposite parity. So this is for K equal to 3. So now we go to K equal to 4. Here, in this case, when L is 3 and I equal to 2. So this is the curve x plus 1 into x plus 3 into x plus 4 equal to y cube. That is the curve. So here we are able to say that if there is a solution, then each term is a perfect cube. We are not able to rule out this possibility. So this is the result for K equal to 4. When K equal to 5, L equal to 2, I equal to 2. So again, you notice that this is a cubic case. Here again is the square case. There are infinitely many solutions in this case. And some non-trivial solutions are listed here. Have a look at it. And K equal to 7, L equal to 2, I equal to 2 again. You have one solution, xy, given by minus 37 by 7 plus minus 2 power 4 into p cube into 5 by 7. So apart from these solutions that we have listed here, for all other values of k, with k lying between 3 and 8, I lying between 1 and k, and L greater than or equal to 2, the equation 3 has no rational solution. So we could solve it completely for 3 up to 8 with one term missing. Okay. So let me now give some important ingredients that go into this result. So just as I explained for the curve with all terms present, same way you can convert the curve with one term missing into a product in arithmetic progression with one term missing, like this. So z into z plus d up to z plus I minus 1 into d. Z plus I plus 1d up to z plus k minus 1d will be now a perfect Lth power. Okay. So first we observe by mirror image that I can be taken to be less than or equal to 3 by 2. In the very first half we can take. The result will be similar if I take it in the other half. And I not equal to 0. These are already done. Thus, every equation gives rise to k by 2 minus 1 equations as I varies. So here itself the difficulty starts from considering all the product and with one term missing, because the missing term can vary from here, this end to this end. So it gives rise, one equation gives rise to several equations. And it can be seen that each term is almost an Lth power. If I take a particular term here, z plus rd, you can write it as ar into xr power L with the greatest prime factor of ar less than k. This is because by this equation, the length of this product is only k. So any prime greater than or equal to k can divide at the most one term here. And by this equation, it has to divide that term to an Lth power. So the primes which appear not to an Lth power can only be primes less than k. Okay? So I can write z plus every term here like ar into xr power L with the greatest prime factor of ar less than k. Okay, so your main task is to form suitable ternary equations of signature LLL or LL2 with L greater than 3 and apply modularity methods to show that these equations have no non-trivial solution. So how do we form LLL equations? So you observe that given any three distinct terms from the product, say z plus qd, z plus rd, z plus st, we can find relatively prime non-zero integers, lambda q, lambda r, lambda s, for which you can get an identity like this. Lambda q into z plus qd plus lambda r into z plus rd equal to lambda s into z plus st. It's like, just like if you have x plus 1, x plus 2, x plus 3, then x plus 1 plus x plus 3 is twice x plus 2. With some more calculations, you can always find for any three terms like this. Okay, so now you put a as capital A as lambda q into a, because I have written this as aq into xq power L. This as AR into XR power L, this as AS into XS power L. So you just put A equal to lambda Q AQ, B as lambda R AR, C as lambda as AS, and UVZ as XQ, XR, XS. Then you have the equation AU power L plus BV power L equal to CZ power L. And we have some control over the coefficients also. The P of ABC, the greatest prime factor of these coefficients, is less than K. So this is a ternary equation of signature LLN. Okay. Now for the signature LL2, this is useful when we deal with the large values of L. If P, Q, R, and S are all integers not equal to I, because that ith term is omitted. So we have to choose not equal to I, with 0 less than or equal to P, less than Q, less than or equal to R, less than S, less than or equal to K minus 1. And this is the important condition here. P plus S equal to Q plus R. Then I take this product Z plus QD into Z plus RD minus Z plus PD into Z plus SD. This turns out to be QR minus PS into D square, which is not 0. This leads to a ternary equation of the form AU power L D B power L equal to CZ square, because D square comes here, with the greatest prime factor of A, B less than K. And the signature of this is LL2. Okay. Now let me say the case when the GCD of L and K minus 1 equal to 1. I already told you that we need not assume L greater than K. Even if you have this relaxed condition, GCD of L and K minus 1 is 1, then your common difference is going to be an Lth power. Okay. And in this case, we can treat the above ternary equation, that is the equation that I got here. So this Z is nothing but D, but it is now D power L. So it is D power 2L I'm getting on the right-hand side. So I can treat it as an equation with signature LLL or LL2. Okay. And also in that case, I do not need 3 terms to form such an LLL equation. Even if I say 2 equations and subtract them, it is going to give rise to an LLL equation. And that, because you can just take the difference and I get this. Okay? And this gives us more freedom in forming ternary equations. And in fact, we can show this result. So if our equation holds, then and if it has a rational solution for 4 less than or equal to K less than or equal to 8, then GCD of L and K minus 1 has to be greater than 1. If it is equal to 1, then it has no rational solution. That much we can prove. Okay. Let me now say about the modular approach here. So since K, we have restricted ourselves to K less than or equal to 8, you know that we can form ternary equations with the greatest prime factor of ABC, the coefficients, less than or equal to 7. And we need to juggle among the terms, use combinatorial arguments, and form suitable equations so that modularity methods can be applied. And plenty of results are available on such generalized Fermat type equations. For L greater than or equal to 11, we were able to apply results which are available in literature already. For L equal to 7, we came across several new equations. I shall explain with one example. For instance, you consider ax power 7 plus by power 7 equal to cz power 7, and abc xyz non-zero integers, ax by cz co-prime, and 43 dividing XYZ. And let us also assume that A, B, C is of this form: 2 power 4, 3 power beta, 5 power gamma, 7 power beta, and 7 not dividing beta, gamma, delta. So I'm just giving one instance where we had to really do the calculations and get rid of the. So suppose XYZ is a solution to this equation. We form the Frey curve. Y square equal to x into x minus a x power 7, x plus b y power 7. The radical, this rad2 means product of odd prime divisors of ABC. It is 105 in our case. And by Ribet's level lowering, the conductor NE of this curve E is 2 power t into 105 with t 1. So NE is 105 and or 210. I'll just explain the case 105. So these are standard procedures. It is known that the Galois representation coming from the action of GQ on the L torsion points, EL, it arises from a new form F of weight 2 and trivial Nebel-Typus character with level NE. So let us do this calculation for NE equal to 105. The dimension of F is 2, and the Fourier coefficients of this new form, let them be Cn in a number field Kf. Okay? And it turns out that C43, but I'm going to choose the prime P as 43, C43 as 4 or 4 root 5. Okay? And this is well known. These are all well-known facts, in fact, for experts. Suppose P divides XYZ, the Frey curve has a multiplicative reduction at P. And also if P does not divide L into N, then we get a trace at the Frobenius as plus minus P plus 1. So the norm of CP plus minus P plus 1 is congruent to 0 mod L. So now you choose your P as 43, L as 7, and NE as 105. Then we get 7 divides this norm. Okay. This gives 7 divides 48 or minus 40. In this case, C43 equal to 4, or it divides 44 square minus 8. And that is a contradiction. Okay. And for n equal to 210, it is similar, but a little more work is needed. So here we have taken all our data from William Stein's database called LMFTB, the L functions in modular form database. So that is for the case L equal to 7. The case L equal to 3, we use an old result of Selma on cubic equations of the form xq plus ayq plus bzq equal to 0. It's a beautiful long paper by Selma, and he has tabulated the solutions for these type of equations for various values of AB. So with the help of that result, we could exclude various possibilities. Now the case L equal to 2, I'm going to explain with 3 examples. So let k equal to 4, I equal to 2. We have the curve as x plus 1 into x plus 3 into x plus 4 equal to y squared. Okay, this is the curve. And this is an elliptic curve of rank 0, and the torsion points belong to Z2 cross Z2, leading to the only solution with y equal to 0. Right? Okay, so this is one typical example. So many cases can be ruled out by showing that the elliptic curve that arises has rank 0 and okay. Now the k, let us go to another example. Let k equal to 5, I equal to 3. then you have the curve x into x plus 2 into x plus 3 into x plus 4 equal to y squared. Okay, in this case, it is birationally equivalent to this elliptic curve y square equal to x cubed plus 8x square plus 12x. And this curve has rank 1. And the model Weyl group of this curve is isomorphic to Z2 cross Z2 cross Z2. The non-trivial rational points of F lead to infinitely many solutions. So this is the one curve which produced infinitely many solutions coming from the
2nth powers. So that looks rather odd, but we shall see this kind of equation coming up soon in the context of surfaces. So actually, this is a pretty hard problem. I think if you write R of capital N for the total number of solutions, then the sort of naive heuristic you might come up with suggests that there should be capital N to the exponent 2 over n minus a half number of solutions over n minus and so in particular number of solutions. Is that not working? Oh, there. So in particular, you don't really expect there to be very many solutions unless this exponent n is small, at most 3. Yeah, we're still unfortunately pretty far from being able to handle even the case n equal to 2. So that's a sort of fairly classical problem. Let's talk a little bit more generally about surfaces. And for this kind of problem, as I say, it'll arise later. It's hopeless to try and prove any kind of asymptotic formula or even a lower bound. So we will be contenting ourselves with rather weak upper bounds. Our expectations are going to be kept very low. So just to give a bit of general context about surfaces. So these are dimension 2 algebraic varieties. And when they're defined over the rational numbers, there are some very basic questions that we could ask. And this has motivated an enormous amount of research around Diophantine equations. So I'm typically going to keep with projective surfaces. So if you like, questions about solubility over the rational numbers is the same thing as solubility over the integers. And that first question is really just whether or not there exist rational points on the surface, or if you like, equivalently, do there exist non-trivial integer solutions to some corresponding Diophantine equation? That's a very basic question. If there are solutions, you can go further. You could ask, is that set of solutions dense? Is it dense in the Zariski topology? Or is it dense in the adelic topology? So in other words, for example, is it dense in the reals? If you pick any real point, can you always find a rational point which is close to it on this surface? And finally, the other question, which will really be the theme of the talk, is if there happen to be infinitely many solutions, can you say something about their distribution? So if you fix a height, can you count how many points there are of that height? So before we get on to the actual surfaces that the focus of this talk, let's have a couple of examples. So this is a surface that I've come to love. It's a Chatelet surface. It has a nice affine equation where you're thinking about a reducible cubic polynomial being represented as a sum of 2 squares. And that's a picture of it. This was drawn by Emmanuel Père a few years ago. And so this is a surface that I looked at with Emmanuel Père and Régis de la Bretèche a number of years ago. And all of the dots on that picture represent rational points, solutions to the equation. So certainly we see some dots. So therefore, the answer to the first question is yes. It's not hard to show that the set of rational points is dense in the Zariski topology. They don't all lie on some finite collection of curves. And so the answer to the second question is yes. They are not dense in the adelic topology. So there are two connected components of the surface, and the black dots correspond to some certain two-adic condition on the denominator of the rational points, and the white spots have the opposite two-adic condition. So it would be impossible to approximate simultaneously a real point on the left hemisphere and a two-adic point on the right hemisphere with a rational point. And this was one of the surfaces that we could actually count points on using universal torsors. Here's another example. I think if you look up Manin's conjecture on Wikipedia, this is the picture you see. It was drawn by Ulrich Derenthal. It's a cubic surface. It's the unique cubic surface with all of its 27 lines visible. In particular, it has many rational points. So the answer to the first question is yes, there are points. Yes, the points are dense in the Zariski topology. And in fact, yes, we know that the points satisfy weak approximation, meaning that they're dense in the adelic topology. And here, unfortunately, we're very far from being able to count points accurately on this surface. So there's a nice result of Heath Brown where he produces an upper bound, but it's still quite far from the truth, the expected truth. Here's a further example, which is much easier to study. This is the Cayley ruled cubic. So it has a double line, and that allows a fibration into lines on this cubic surface. So this was something that I looked at with Per Sauberger and again Régis de la Bretèche. And again, there are infinitely many points. They're dense in either topology, and we can count points. And actually here it's much easier to count points, and it's kind of interesting that you don't get an Euler product appearing in the leading constant. It's a slightly more complicated constant. Okay, so these are the surfaces that I wanted to talk about in this talk. I'm going to call these surfaces hyperelliptic surfaces. They have an explicit equation, y squared is equal to x to the n plus x times a binary form f in u1 and u2 plus a further binary form g in u1 and u2. And the difference here is that we are counting these variables with different weights. So it lies in some weighted projective space. So u1 and u2 have weight 1, x has weight 2, and y has weight n. And we view the entire surface as something of degree 2 times n. So we need to ask the binary form g to have the right degree, namely 2n, and f to have degree 2n minus 2. So this is what I'm going to be interested in looking at. As I say, it has degree 2n in this weighted projective space. There's a fibration down to P1, and its fibers, the smooth fibers have positive genus. And interestingly, with these surfaces, there is always a distinguished rational point. So this first question always has the answer yes. So you can take the point x equal to y equal to 1 and u1 and u2 equal to 0. And that always lies inside the surface. And that's about the only thing we know. So the remaining questions are unknown. So firstly, this question of Zariski density. That is, I guess we don't know, but it's conjectured to be not Zariski dense. But if n is equal to 3, that is a big conjecture in the area. I'll say more about the special case n equals 3 shortly. Is it dense in the adels? Is it dense in QP, for example? Again, I don't think we expect that to be true for large n, but when n is equal to 3, this is a big conjecture, and it falls into the scheme of the Brauer-Manin obstruction. And finally, can we count points? Oops, sorry, I didn't mean to do that. Can we count points of bounded height on this surface? Well, yes, in the sense that we can count points of bounded height on weighted projective space. But as soon as we've got an equation like this, we're not able to do anything particularly impressive. Now, the case n equal to 3 has its is really familiar as a particular kind of rational surface called the Del Pezzo surface. And if you look up Del Pezzo surfaces in Hartshorne's algebraic geometry book, he defines these things as surfaces of degree D that lie inside projective D space. And in particular, he requires D to be between 3 and 9. So the case D equal to 3 is the case of cubic surfaces. D equal to 4, these are intersections of two quadrics. But he more or less refuses to admit the existence of lower degree Del Pezzo surfaces. But they do exist. They just lie in weighted projective space. So the case n equal to 3 really is a degree 1 Del Pezzo surface. And I guess the mantra for these things is that the analysis of these surfaces, the arithmetic of these surfaces, becomes harder as the degree gets smaller. So in fact, degree 9 corresponds to projective space, which is very easy to analyze. And degree 1 is kind of like the hardest example of a Del Pezzo surface. So in some sense, it's not so surprising that we can't say very much. I came across this quote of Swinnerton Dye, which I thought was quite amusing. So he was pointing out that surfaces of degree 2 and 1 have no aesthetic merits, and they've attracted very little attention, and we should basically ignore them until we've understood what goes on for the interesting case of cubic surfaces. So I suspect that this talk won't do anything to disbar you from that opinion. Okay, let me say a few words about Zariski density, because I think that's a very interesting topic at the moment. There's been a lot of recent work. So this is the case n equal to 3. I'm writing out again what the surface looks like. It's y squared equal to x cubed plus x times a binary quartic form plus a binary sextic form. And these surfaces have a nice elliptic fibration down to P1. So the fibers are all genus 1 curves. So you can ask about Zariski density of points. It's conjectured that that the rational points are always Zariski dense. We always know that there's at least one, as I've already mentioned. And there's been a number of approaches towards proving Zariski density. So there's a paper I like from over 10 years ago now by Tony Varily Alvarado. So he has to assume that the Tate-Shafarevich group is finite, so that's conditional. And under that assumption, he can invoke this work of the Dockchester brothers, which gives you the parity conjecture, to show that under certain assumptions on F and G, you get Zariski density of rational points. So he studies, obviously variations of root numbers of these particular families of elliptic curves. And I think it involves some nice sieves in the argument. So it's a fairly analytic argument. But there are other approaches, and just in the last few years, there's been some quite spectacular work by Rosa Winter, particularly, and Julie Desjardins and Nashkreki, using kind of different techniques to handle more cases, which we can show to be Zariski dense sets of rational points. But in this talk, I'm going to be counting. It's more to do with upper bounds. So let's say explicitly what the counting function is. So again, this is the equation. These are the hyperelliptic surfaces that we want to try and get some handle on. And motivated by the weights in the projective space that it lies in, we define a slightly funny looking height function where we take the maximum of the modulus of u1 and u2, x to the half, and y to the 1 over n. So this is assuming that we've got basically integers y, x, u1, and u2, which are solutions to this surface. So that's all we're doing. We're just counting the number of integers u1, u2, x, and y, such that this max function is bounded by b, and which satisfy the Diophantine equation at the top of the slide. So what can we say about this counting function? Well, before I get on to the approach that Dante and I were using, we can say something quite simple using a famous result in the literature. So the Bombieri-Peeler bound from 1989, it's proved to be very powerful, and its generalizations have had a huge impact on analytic number theory at large, I would say. But all we need here is the original version, which says that if we have an irreducible polynomial of degree n, let's call that capital F with integer coefficients, and we count the number of zeros to this polynomial in which the modulus of x and y are bounded by p, then this grows at worst like big O of p to the 1 over n plus epsilon. So perhaps that's familiar to you already. Sorry, it's worth, before I go on to the next bit, it's worth pointing out that a crucial aspect of this is that the implied constant really only depends on epsilon and on n. It does not depend on the coefficients of f. So it's a uniform bound, and that's crucial. So here I've written out again what the counting function is. And under the well-known fact that any mathematical talk should have a proof, we can easily prove this lemma. So this counting function that we're interested in is at most b to the 3 plus epsilon. So what do we do to get that? Well, all we do is we just fix u1 and u2. And then we've got a polynomial in x and y. Unfortunately, y is allowed to go all the way up to b to the n. So the 1 over n saving we get from the Bombieri-Peeler bound is more or less annihilated. And so for each u1 and u2, the Bombieri-Peeler bound gives a contribution of b to the 1 plus epsilon. And we have b squared values of u1 and u2. So overall, that gives us our b to the 3 plus epsilon. Okay, so that's our initial attempt at an upper bound, and the goal is to try and prove something better than that. Okay, well, actually, that's quite far from the truth, at least if n is equal to 3. So if n is large, I guess we expect it to be even further from the truth, actually. But for n equal to 3, we certainly expect there to be infinitely many solutions. And so here you have to remove some exceptional curves, some accumulating subvarieties. There happen to be 240 of these exceptional curves that you can identify. And the conjecture, or a special case of this conjecture, is that if you remove all of those curves and count everything that's left, it should grow like b, not b cubed, b times some small power of a logarithm. Well, upper bounds are quite hard, it turns out, in this setting, but lower bounds are a bit more approachable, at least if you assume a little bit more about the geometry of the surface that you're looking at. So, for example, if you assumed that all of the 240 exceptional curves were defined over the rational numbers, then that would be enough to apply this result of Christopher Fry, Dan Loughran, and Efthymios Sophos from a few years ago, which gives you a lower bound which matches the prediction of Manin. However, it's a rather special situation that it applies to, and if you picked a completely random Del Pezzo surface of degree 1, or a particular surface with n equal to 3, I don't think we even know how to improve the lower bound 1. So we're quite far from understanding what's going on for typical Del Pezzo surfaces of degree 1. So minimal here means that the rank of the Picard group is 1. That is so big S is Z. I think that's an open question. Well, I think we're not even, so each exceptional curve which happens to be defined over the rationals contributes b squared. So that's why they're removed in the formulation of the Manning conjecture. But if you allow them, we would certainly then expect that there is an upper bound of the shape b squared for the total number of points on these surfaces. And that's, I think that's still far from what we're really able to do unconditionally, but I leave it as a question. Is it true that this is big O of b squared for any s? That's probably true, but difficult. Now, we can sort of, in certain cases, squeeze a bit more out of the Bombieri-Peeler argument, and I did want to mention this because I think it's quite pretty. Now, the problem with the Bombieri-Peeler bound is, although it's very uniform, we can't hope to improve it in any generality because it's not hard to see that it's optimal up to the epsilon, at least, in genus 0. So if you take the curve y squared is equal to x cubed, then you can parameterize all of the solutions. They will look like y equal to t cubed, x equal to t squared. And if you just count up how many you've got of those in the box minus p to p squared, then you get p to the 1/3. Okay, so the Bombieri-Peeler bound is tight in genus 0, but we're trying to apply it to higher genus curves. We're trying to apply it to integer points on elliptic curves. So actually, this point of view was exploited by Harold Helfgott and Akshay Venkatesh back in 2006. And they observed that on the one hand, if the coefficients of these curves is large, there's actually a little tiny bit of extra saving that you can exploit in the Bombieri-Peeler method. So Diophantine equations or polynomials of large height tend to have fewer solutions, and you can make that quantitative and put it into the Bombieri-Peeler method. On the other hand, that should be C4 and C6, if the coefficients are small, then you can look in the Mordell-Weil lattice following a strategy of Mumford. So Mumford was the sort of proved, had a very nice paper where he, before faultings, was able to count rational points of bounded height on higher genus curves by exploiting repulsion in the Mordell-Weil lattice. And I think he proved something like log b as the number of points on a curve of genus 2, for example. I mean, now we know that there are finitely many, but the underlying ideas inside can be exploited here to show that if you have an elliptic curve of small height, there is a repulsion among the integer points on this elliptic curve. And that allows you to get an extra saving in that case. So you can combine these two points of view. This was done, for example, by Mendes da Costa, a student of Harold Helfgott, a number of years ago. And he was able to show, using this point of view, that you could save a tiny power. I don't think he made it explicit, but before we had 3 plus epsilon, but if you carry this plan out, you can get 3 minus delta. And actually, if you're prepared to assume, make some standard assumptions about the growth of ranks on elliptic curves, you can get quite close to that question that I mentioned on the previous slide. So you can prove b to the 2 plus epsilon. So I think this would follow probably from Birch, Sunit, and Dyer, and some other stuff. All you need to know is that the rank of an elliptic curve grows like little o of the logarithm of the conductor. So if that was true, that would be enough to prove that b to the 2 plus epsilon bound. So there it stood for a number of years, but just recently, in a very impressive multi-author paper which concerned a large, well, had a large number of results in it, despite its very short length. They were able to produce better explicit upper bounds for the ranks of elliptic curves in the spirit of this hypothesis that I mentioned. And using that, so this was work of Bhargava, Shankar, Taniguchi, Thorne, Zimmerman, and Zhao. Using that and feeding it into some of the earlier work on this topic, they were able to get quite an impressive value of delta. So they were able to prove the upper bound b to the 2.87. So this is very, very recent. But let me just emphasize, this is all for the case n equal to 3. So let me then go back to the general case. So this is degree 2n hypersurfaces in this weighted projective space. I think we're assuming here that n is odd. And what we were able to prove was an upper bound of the shape b to the 3 minus 1 over 20 times log b squared. So our goal was to try and produce a sort of an explicit value of delta in the spirit of the previous slide, but also have an argument which carried over to arbitrary hyperelliptic surfaces of the shape at the top of the slide. So numerically, unfortunately, this is quite a bit worse than the multi-author paper that I had on the previous slide in the case n equal to 3. But perhaps on the other hand, it's completely uniform. So this implied constant really only depends on n and nothing else. But more importantly, the strategy that was in that Bombieri-Pila ++ slide completely breaks down when n is not 3, since we don't have the same kind of uniform bounds for ranks of Jacobians of hyperelliptic curves. So the proof, I wanted to spend the rest of the talk just going over some of the steps in the proof, and it won't have anything to do with elliptic curves. It'll be just a question in sieve methods and exponential sums. So the goal is to try and detect squares in this particular sequence of omegas. So remember, maybe it's worth flashing up the previous slide one more time, because you can see that we are trying to look at an equation, y squared is equal to x to the n plus blah, blah, blah. So really we're trying to detect when the right-hand side is a square. And that's something that we can do if we're interested in upper bounds. There's a very nice upper bound square sieve by Heath Brown. And this works for any sequence and gives you an upper bound for the number of squares in that sequence in terms of the average of this omega function, and then a kind of average which is weighted by Legendre symbols. And actually, one of the advantages of this is that you have a lot of flexibility over the choice of primes that you're working with. You can really work with an arbitrary set of primes. So again, the proof of this is actually, it's only really 1 line, 1.5 lines. You just play around with this expression here. So omega of m times the mean square over the Legendre symbols m over p. So the point is that we're taking a square, so that term in the summand is non-negative. And if you play around with it, you recover Heath Brown's square sieve. Now, unfortunately, if you apply this, it doesn't help. It gives you a worse than trivial bound for ns of b, unfortunately. You need to do something a bit more sophisticated. And for that, we could turn to a variant of the square sieve, which was developed by Lillian Pearce, I think while she was a master's student of Roger in Oxford. And it's unfortunately a bit more complicated to look at. The key fact is that it allows you to work with 2 different sets of primes. curly P and curly Q. You can kind of see that the first term looks a lot like the first term we had on the previous slide. It's just an average of the omega. And the second term has the same kind of structure as the one on the previous slide. It's just what we have Legendre symbols made up of a product of 4 primes now instead of a product of 2 primes. Okay, so the ability to choose primes is going to be crucial in what's to come. We will be choosing the set curly P to be a set of primes of size capital B, the set curly Q to be a set of primes of size capital Q. We'll make some assumptions about the sizes, relative sizes of capital Q and capital P. I've written down what the eventual sizes are, but I don't think we're going to worry too much about explicitly balancing terms in this talk. We can very easily look at the first term. I've left out all the middle cross terms. You have to deal with those as well. But the first term is pretty easy. The size of curly P is roughly P over log P. And the size of curly Q is roughly Q over log Q by the prime number theorem. And the size, the average of the omega function, well, U1 and U2 go up to B, and X goes up to B squared. So we get B to the 4 for that M sum. So you can kind of see that we're shooting for something which is less than B cubed. So we'll certainly need the product of P times Q to be bigger than B for this term to be acceptable, let alone the remaining terms. So anyway, let's talk about the remaining terms. So the inner, if you like, oscillatory sum that one has to think about is this sum of omega M against the Legendre symbol, M over PQ, P prime, Q prime. And then I've just written out what that gives you when you substitute in omega. So it's really just a summing over the values of this polynomial. And what we need to do is get a good bound for this, which is valid for typical values of P and P prime being distinct and Q and Q prime being distinct. So that's a concrete problem that we have to solve. We are going to break into residue classes modulo R in a familiar way. So we're going to break for X into residue classes modulo R, where R is the product of the primes. So we get a sum over alpha mod R, and then we need to, because the Legendre symbol, it really only depends on the value of alpha mod R. And then we need to detect how often X is congruent to alpha mod R. And we're going to do that with additive characters. And when you rearrange the sum, you're left with a sum U and a sum G. And the sum U is this sum over U1 and U2, and the sum over alpha mod R, and the Legendre symbol involving alpha U1 and U2, and twisted by this additive character. And the G sum is easy to analyze. It's just a geometric series summed over little x. So G is easy, and the effort is now directed at understanding the size of U. So U, capital U, is a sum of exponential sums, a sum of complete exponential sums involving alpha. So can we get a good upper bound for this, for typical values of C and typical values of R? So the whole reason for introducing these two different sets of primes of differing sizes was to facilitate an application of the so-called Q analog of van der Kolk differencing. I've written out what the sum U is again, and I'm going to factor R as R0, R1, where R0 is the product of primes from curly P, and R1 the product of primes from curly Q. So the point is that these exponential sums satisfy multiplicativity. That's important. So we can factor them as the exponential sum involving R0 and the exponential sum involving R1. And that allows us via this, maybe I won't go through it in too much detail, but it's fairly standard. It's a sort of application of Cauchy-Schwarz inequality with a particular kind of H. You can separate it out into two different sums. There's a sum over U's involving the exponential sum R1, the mean square of that. That turns out to be very easy to analyze here. We can get away with a weaker bound. And the hard case is looking at what I've called here sigma 2. So it's a sum over U and a sum over, and the mean square of a sum over H and the exponential sum involving R0. So I'm sort of, I don't want to exhaust you with manipulations involving Cauchy-Schwarz. So you'll have to take my word for it or check it on a piece of paper that if you, when you have a mean square like this, you can difference it. You can then extend the sum to residues modulo R0. And ultimately, you're led to this exponential sum when you do that. So this is a complete exponential sum modulo R0. It has 4 variables. It has these product of 2 Legendre symbols and a additive character thrown into the mix for good measure. And so the goal now, you can forget about everything else. The goal is to try and get a good upper bound for this. And again, you want to do this for typical vectors H and K. And luckily, there's this same endemic multiplicativity property, which means that we can just fix attention on the case that R0 is a prime. I mean, R0 is a product of 2 primes, but you can look at these 2 factors separately. So we're led to think about a certain kind of exponential sum over a finite field. So now we're in good shape for trying to exploit some standard results about the sizes of exponential sums over finite fields. So that's what it looks like. As I say, it's a 4 variable exponential sum involving a mixture of multiplicative and additive characters evaluated at various polynomials. So let's think about upper bounds for this. So clearly, just to get a size, compare it to the trivial bound for this would just be to bring in modulus signs. We have 4 variables, so that gives us a p to the 4. And we need to get some saving over that. Now, in fact, actually, we can't just get away with any saving. One thing we can observe is we can fix S1 and S2. So if we fix S1 and S2 and just content ourselves with summing trivially over those, then we get a product of 2 exponential sums, one involving alpha and one involving beta. And these are now both one-dimensional exponential sums. And we can appeal to the sort of Bayes resolution of the Riemann hypothesis to show that each of those exponential sums is square root p. So there are 2 of them. And when you combine that with the number of S1 and S2, that gives you the Weil bound, p cubed. So we've certainly able to prove some non-trivial bound for this exponential sum. We did some digging around in the literature. There's a nice paper by Nick Katz where he looks at certain kinds of singular exponential sums in an IMRM paper. But unfortunately, again, when you go through his results, it turns out that that really just recovers the Weil bound in this particular setting. So again, gives you p cubed. Unfortunately, those aren't enough to give you anything beyond the trivial bound. So you really need to go beyond that p cubed. Otherwise, you'll just be back at b to the 3 plus epsilon that we got pretty easily from Bombieri-Pieler. So in some sense, the main result or the main work in the paper was to prove to improve this fade bound. And so that's what we were able to do. If you take generic, well, you just need H1 and H2 and mu1 and mu2 to not all share P as a common factor, then you get P to the 5/2. You save a half. So to end, I just wanted to say a little bit about how we approach this exponential sum. So I think the methods are quite flexible. What I've done is I've encoded the Legendre symbol as an equation. So it's now just features the additive character in the summand, and we're summing over the solutions to these two equations. So I've had to introduce two more variables, u and v, because I'm detecting when that polynomial is a square. So that's a bit awkward to work with. You know, it has monomials of all kinds of degrees there. So it's very convenient to try and make this as projective as possible. Now, this is where it's quite useful to have a particular, or to have an arbitrary set of primes to be able to work with. So I think if we demand that our primes are congruent to 1 modulo n, that allows us to write any element of fp as an nth power. So we can replace u squared by u to the 2n and v squared by v to the 2n trivially. And by, again, the set of non-squares, by using the fact that the set of non-squares, the set of non-zero points in fp modulo the squares is plus or minus 1, we can again reduce to the case that x and y are themselves squares. So that renders our exponential sum a little bit more homogeneous. We have a additive character involving an f, and we have these two polynomials g1 and g2. F has now become quadratic as x squared and y squared, and g1 and g2 is now much closer to being homogeneous of degree 2n. In fact, the first polynomial g1 is homogeneous of degree 2n. The second one has this annoying shift by h. Now, to approach this, we called upon a sort of an approach of Hooley, which builds on Deleuze's work, and it's kind of a convenient catch-all for estimating random exponential sums by reducing the problem to point counting over a finite field, for which we could try and apply sort of Deleuze machinery. So you write down this counting function which depends on tau. So it's the number of solutions. So it's important here that you're working over arbitrary extensions of your finite field. And you count the number of solutions to G1 and G2 both being 0 and f being tau. Then you can conclude that your exponential sum is p to the k over 2, provided that you can handle the mean square of this counting function away from some predetermined nj. So that was the approach that we wanted to take. It's a little bit complicated. We write down the function nj of t, and what we're going to do is just eliminate one of the variables. I guess we're eliminating y using that equation, and we get an intersection of two polynomials. And we are at the same time making it projective so that it's easier to apply standard results by introducing a further variable t. So it's a bit horrible to look at, but it's basically an intersection of two polynomials, very explicit, in 6 variables. And now this intersection is projective. Its polynomials are all homogeneous of degree 2n. And what we can do, so the task, what we would like to be able to do is apply this kind of estimate of Deleuze. So this tells you that if you have any complete intersection, which is projective and defined over a finite field of dimension 3, then the number of points on that complete intersection is q to the power of 3 plus an error term which depends on the dimension of the singular locus of the threefold. So we have an intersection of 2 quadrics in P5. So we have a threefold. It depends on this parameter tau. So if we can get enough control over the singular locus of this threefold, then we can apply this estimate of Deligne, then we can feed it into this argument of Hooley, and ultimately get an upper bound for the exponential sum that we're interested in. So it was a fairly elementary argument, but quite a lot of work was directed at estimating the singular locus, the size of the singular locus for this particular threefold that was on the previous slide. And what we're able to do is show that actually outside finitely many choices of tau, where that finite number is just, it just depends on n rather than q, you get something with isolated singularities. So sigma would be 0 for those. It has dimension 0. And that's what you do. You have to, so you're led to take q cubed for the approximation of this counting function. And then either you have a good value of tau, so something where the threefold has isolated singularities, in which case the error term behaves like q squared. And you get an upper bound for that. Or you don't have isolated singularities, but you can prove that the dimension is at most 1. And so therefore you get an error term of the size q to the 5/2, which is bigger, but there are fewer tau that can lead to this eventuality. So when you look at that, you arrive finally at the conclusion that this exponential sum is bounded by p to the 5/2. Okay, so that is the sort of end of the sketch of the proof that I wanted to give. You will have noticed that this exponential sum has 4 variables that we're interested in. And so the trivial bound was p to the 4. What we were able to prove was p to the 2.5. So I think it's not hard to see that that's not optimal. One might expect that you get square root cancellation if you work hard enough. And we did think about that for some time. We were unable to do it. And then we sort of lost a little bit of motivation because I guess even if you're able to do this, when you work through the argument, you find that actually you would save an eighth. So that would give you this exponent 2.875. But that's still just a tiny bit bigger than that multi-author paper in the most interesting case of n equal to 3. Okay, thanks.
Okay, thanks, Tim. Let's unmute and thank the speaker. Any questions to the speaker?
Yeah, I have a small question, Tim. So in Dante's thesis, you also had done some kind of variant of the square C for more general polynomials. Is that something that would be applicable here, or is there a lack of Lillian's variant?
You would need a variant. Yeah, you would need an analog of Lillian's ideas. But you're right. It would be interesting. I think I was calling it a hyperelliptic surface. That's not the most general hyperelliptic surface you could write down. So rather than detecting a square as we were doing here, you could try and detect it being a root of some more general polynomial for which Dante's thesis ought to be useful if you could develop the sort of Pierce analog. Yeah, no, it's a good question.
Okay, thanks.
Okay.
More questions? Philip?
Yeah, hello, hello, Tim.
Hello.
Great lecture. So about this Van der Korput method, so in the end, it was a two variable or four variable exponential sum. So, but what I am wondering, so I am thinking because there is a general, there is a paper of Pinksy and Jivu with an appendix by Will Sawin, which give a general treatment of the Q Van der Korput method in one dimension. With and probably maybe you know this paper.
No, I'm embarrassed to say I can't keep up.
No. Okay. So it's an archive. But it's one-dimensional. But then they give, so Will gives a criterion relatively simple to make sure that that you can apply A and B as much as you wish. I wonder if with this in mind, when you go to apply Van der Korput, maybe you could design it to be so in this slide. So you see,
okay,
or maybe so you see, apply the Van der Korput in one time in one variable, and then again with the and follow up the transformation and see whether in the end this criterion apply. I don't know.
That's an interesting idea. Yeah, I wasn't aware of that. Thank you.
Let me find just 1 second. Maybe so I'm just because often when you have these horrible multivariable exponential sums, if you do it differently, they get structured, and in the end, you lose the structure when you open everything. So 1 second.
Okay.
Okay. Okay. Just.
Where is it?
Okay. Is it this? Just. Okay. Oh yeah. It should be. It's.
I've put it on the chat.
I just did it.
Yeah, I put it. Where is the chat?
I just did it, Philip.
Okay.
Okay.
So it's an old paper, but he has had many rounds of revisions, and the one involving Will in the appendix is the most useful, I think. And because I see that your object, it has a Legendre symbol and then just a linear polynomial phase.
Yeah.
And it indicates a Fourier transform, of course. So you have done some A processes and then some B. So maybe it can be useful.
Excellent. Thank you. I wasn't aware of that. I will have a look. Thank you.
Thank you. More questions? Think there are no more questions. Okay, let's thank the speaker and all other speakers. And of course, let's sing happy birthday again. So Balu, happy birthday. Enjoy the party later today. And see you after the break.
Thank you. Just 2 minutes of everybody. So a couple of announcements. First is as you said, the felicitation will be at 7 o'clock today, Indian Standard Time. So we have lectures in the next slot, which will be another link. But after that, we have a little break, and 7 o'clock we start the felicitation. That's the first thing. Second thing, we are planning to put these videos on. And any of the speakers have any problem, please let us know, because we plan to put them. And third one is that I request all the speakers, if it is okay with them, to share their or send their slides to us, because there have been a lot of requests for that. So that's the third thing. And I think that's all. So we'll close the session right now, and the next session will start in half an hour, which is another link. Thank you once again, Professor Spalitz, for chairing the session. Thanks a lot. Thank you. Thank you.
Thank you.